given group of the periodic table, for example, group 6A, the atomic radius increases as we move downward. As we move from left to right in any row, the atomic radius generally tends towards smaller values. This occurs because the effective nuclear charge acting on the outermost electrons is increasing. As we proceed across the first long row of the table, in which electrons are being added to the valence shell d orbitals of the metals, we see an overall decrease in radius as a result of increasing effective nuclear charge.
The atomic radius tends to increase from top to bottom. Okay, so at the top you have a smaller atomic radius. As you go down, the atomic radius gets larger. So why is that? That's because going down a column, the outer electrons are further from the nucleus, so the valence electrons. As you go down the columns, your principal quantum number increases, right? So then you have larger orbitals that are further away from the nucleus.
Rutherford's gold foil experiment actually led him to be able to measure the diameter of an atom quantitatively, and he came up with a measurement of approximately 2 × 10⁻⁸ centimeters in diameter. The problem with measuring the size of an atom is that later on, as we developed into the quantum mechanical model, we know that there's absolutely no concrete boundary of an atom. There's no distinct, defined outer edge of an atom. So we can really only approximate the true measurement of the size of the atom. And one way to do that is we measure an atom's atomic radius.
Moving down a group in the periodic table, the number of electrons in filled electron shells increases, but the number of valence electrons remains the same. The outermost electrons in a group are exposed to the same effective nuclear charge, but electrons are found farther from the nucleus as the number of filled energy shells increases. Therefore, the atomic radii increase.
Miss Naugle, I know what an atomic radius is.
Great. Now I can give you a stamp.
Sweet.